Guys, and welcome to the video. Today I'm going to be showing you how to calculate critical power using the linearized hyperbolic two-parameter model. Now, I want to start off with a disclaimer of this video. This video is not going to be a review of critical power physiology. It's not going to be a review on how to use critical power in training. And it's not going to be a review on the applicability of the certain model that I'm calculating today, even though there are plenty that exist. And some people might think that some methods are better than others, but today I'm simply just showing you how to calculate this two-parameter model. The purpose of this video and the reason I kind of did this video was that when I first got into understanding critical power, I've read many papers on the topic, and some of them show you how to calculate it, and some of them don't. They kind of skip over how to calculate it. So I feel like people can read peer-reviewed papers. However, it might be hard for them to understand. And most people, when they don't understand something from like a peer-reviewed paper, they try to find a simpler resource, and sometimes YouTube happens to be the place that you go to try to find simpler resources. And even in my time and looking for videos on critical power on YouTube, I haven't found any videos that walk you step by step on how to calculate it for yourself using something like Excel. So that's what I plan on doing today, and I hope you enjoy the video. So a little bit of background on what we're doing is, like I said, I'll be going over the linearized hyperbolic two-parameter model. That's, in simple terms, taking this hyperbolic relationship between power and time, or speed and time, it would also have the same relationship, and then converting it into a linear regression so that it's easier to calculate the two parameters of critical power and W prime, or if you're using speed, critical speed and D prime. So that's all I'm doing. Let's jump into it. So you can see here that I've collected various tests from a runner. So I said, okay, here's 600 meters. I need you to run that as fast as you possibly can. And then I timed it, and that's the time it took them to complete 600 meters. 800 meters, that's the time it took them. 1,000, and so on and so forth. Hopefully those are on separate days, because all of these need to be really high effort attempts. So once we have these data, we can put them into a chart and just make sure you label which one's the y-axis and which one's the x-axis. So in this case, we can calculate critical speed in meters per second as the slope of a linear regression, which in Excel makes it really easy for us. Instead of doing the least squares method longhand, we can just type in slope, and then I click tab to get it to open up like this. And then you highlight your known y value, which is going to be distance, and then highlight your known x value, and then click enter. So that's going to say our critical speed is 5.4 meters per second. The next thing we got to calculate is D prime, which, if you're not familiar with the critical speed version of critical power, this is basically the substitute for W prime. So this is going to be our y-intercept. So here you go, intercept, tab again to make it complete the function, and then highlight your known y, comma, highlight your known x, and enter. Okay, so that is our D prime. Something else you can do is, if you're looking at this speed and you're like, okay, I don't know what that means, because my activity monitor tells me my pace in minute per kilometer or minute per mile, or how many minutes per kilometer, how many minutes per mile. You can also convert that too. So you can do that by going time, comma, comma, 3, 6 here. And then you want to convert this into miles per hour times 2.237. And I simply got that number, this 2.237, from the fact that there's 2.237 seconds per meter per second. Okay, so once you type that in, you'll notice that it's 00 because the format is number. And since pace is a form of time, we need to customize that format. Hopefully I'm not going too fast for y'all. See, minutes to seconds. And there you go. So now we have our critical pace, hypothetically speaking, which is going to be a 4-minute, 57-second mile pace. So the next thing we can do is we can calculate, basically just rearrange the y equals mx plus b equation to find out a bunch of different variables. So in this example, we're going to try to find how long it's going to take you to complete a race distance. So in this case, it's going to be how long it's going to take you to complete a 5K. So we're going to go equals the known distance minus d prime all divided by critical speed. And as you can see, it says in a 5K, this particular person with this particular effort is going to complete a race in 912 seconds, which I believe is like 15 minutes and 12 seconds, something like that. So next, we can do the opposite of that. And that's just simply critical power, or critical speed, rather, times the known time plus d prime. And there you go. So the last one here is not necessarily a rearrangement of this same y equals mx plus b. However, this does work as well. And at the end, I'll tell you, I'll show you 2 papers, and one of those papers actually shows you this equation. So this one's equals d prime multiplied by the inverse of the known time, all plus critical speed. And there you have it. So if I want you to work for 180 seconds or 3 minutes, then it's saying that your best possible speed is going to be 5.8 meters per second. So let's say I wanted to make it like 200 seconds, right? Or let's say, actually, I want to make it like 60 seconds, right? Then it's going to say 6.6 meters per second is going to be your best pace. If I wanted to go 120, so 2 minutes, then it's going to say 6 meters per second. So as you can see, you can play around with that and use it however you want to. Next, let's come over here to the example of a cyclist. And let's say they did the exact same thing where we had a cyclist perform some constant intensity testing and just basically went to exhaustion and then timed how long it took them to get to exhaustion. So as you can see here, these are the watts we had them work at, and then this is how long it took them to fatigue at various constant intensity watts. So you'll notice something about the power to time relationship, like I said in the beginning, is hyperbolic in nature. So in this case, we have to take the hyperbolic 2-parameter model and then convert it into linear, just to simplify the calculation of critical power and W prime. So in doing so, we have to convert the time into an inverse time relationship so that this can be linear. In doing so, we actually flip around the roles of critical power or the location of critical power and W prime in the linear regression equation. So instead of being the slope, critical power is now going to be the intercept. However, the way you calculate it is the exact same thing. There you go. Equals slope instead, comma, and there you have it. Same thing as before, these equations to the right, just like the equations to the right over here, are what I use to calculate these variables. These equations to the right are what you'd use to calculate these unknowns. So let's go ahead and do that. You got to put parentheses to make sure that happens first. Okay. So if I worked at 200 watts, it's going to say you're going to fatigue probably in this many seconds. And let's go ahead and finish up with this one. Actually, in this case, we don't need to do that. And if I wanted you to work for 3 minutes, that's the highest possible wattage that you most likely could complete it at before exhaustion. So that's pretty much the end of the video. This is how you would calculate it yourself. Again, I'm not going to go into how many tests you need or what the test environment needs to be like, where you get your test data from. I'm just saying, okay, if you have this data, this is how you calculate it. So feel free to use that however you want. An example of how to do it up nicely is here, like a little dashboard for a particular athlete named Bob in this case. If this guy's a runner, Here's his data that I had him do. I wanted him to run, certain distances, and these are his times. This could also be historical data. This could be like his best times in races that he's done, as long as those races are fairly recent. And I can type those in, and then I can do the exact same thing where I calculate the critical speed and d prime and all that good stuff. So as you can see, there's just so many ways to kind of really do whatever you want with this in order to best serve your athlete or best serve yourself if you're using this as a training tool for yourself. So in closing, like I said earlier, a lot of papers can make calculation of critical power or critical speed kind of complicated. However, in all my reading, these are two papers in particular that made it super easy, like for me at least, made it extremely easy to understand. So if this video didn't help you today, I highly suggest you go find these papers. And if I couldn't help you, these papers definitely can. Yeah, so I guess that wraps up the video. Be on the lookout for future critical power and critical speed videos, including physiology and including how to use it in training, and maybe even some more mathematical calculation models here in Excel using different things like the 3-parameter model, or how we can use the 3-minute all-out test to then calculate critical power used in interval training and things like that. Hope you enjoyed the video. Have a good one.